Eigenvalues and Eigenvectors. The idea of an eigenvector is if you take a square matrix A and multiply by any vector, the vector either changes or it doesn't change. If it changes, but it maintains the same direction, then that vector is an eigenvector with respect to matrix A. So for a square matrix A, an eigenvector V is a non-zero vector such that when A operates on V, the result is proportional to V. So A times V is equal to some scalar lambda times V. Lambda here is called the eigenvalue corresponding to V. Eigenvalues are found by solving the characteristic equation determinant of A minus lambda I equals 0. So let's take an example. A matrix A, 2, 2, negative 4, and 8. And let's look at vectors V, 1, 1, and W, 2, 1. V is an eigenvector of A, since if we take A and multiply by V, we get 2 times 1 plus 2 times 1 is 4. Negative 4 times 1 plus 8 times 1 is 4. So we get the vector 4, 4, which is 4 times vector V. If we take A and multiply by W, we end up with the matrix 6, 0, which isn't a multiple of W. Okay, so how do we find these eigenvectors and eigenvalues? We have to start by solving the determinant of A minus lambda I equals 0. So for the matrix A, 5, 2, 2, 1, this means finding the determinant of 5 minus lambda, 2, 2, 1 minus lambda. Well, this determinant is, of course, 5 minus lambda times 1 minus lambda minus 2 times 2. And when we expand that, collect like terms, we get lambda squared minus 6 lambda plus 1. Using the quadratic formula, we end up with lambda equals 3 plus or minus 2 root 2. Those are the eigenvalues associated with this matrix. Let's try one where we find the eigenvectors themselves. Again, we take our matrix 2, 2, negative 4, 8, and we solve A minus lambda I equals 0. Much in the same way as we did in the previous example. We end up with the determinant of 2 minus lambda, 2, negative 4, 8 minus lambda. So that's 2 minus lambda times 8 minus lambda plus 8, or lambda squared minus 10 lambda plus 24. And this, of course, factors, or use the quadratic formula to get lambda equals 6 and 4. Now, once we have those values for lambda, we can go ahead and stick each of them into the A minus lambda I separately. So if we have lambda equals 6, A minus lambda I is 2 minus 6, 2, negative 4, 8 minus 6, or the matrix negative 4, 2, negative 4, 2 equals 0. So negative 4x plus 2y has to equal 0. Or that 2x equals y, or the eigenvalue 1, 2. Similarly, when lambda equals 4, we get negative 2x plus 2y equals 0, or x is equal to y. And that eigenvalue is 1, 1. Another example. We'll find the eigenvectors for 5, 2, 2, 5. First, we solve a minus lambda I equals 0. The determinant is lambda squared minus 10 lambda plus 21. And so we get lambda equals 7 or 3 by the quadratic formula. So for lambda equals 7, a minus lambda I is negative 2, 2, 2, negative 2, or that x is equal to y. So we get the eigenvalue 1, 1. For lambda equals 3, we have 5 minus 3, 2, 2, 5 minus 3, or 2, 2, 2, 2, which gives x equals negative y, or the eigenvalue negative 1, 1.